No, tractability again. You'll recall that last time we were looking at what happened when we added cities to our brute force algorithm for traveling salesman problem. And we found that growth was a massive problem. It wasn't just that the numbers got big, it's the way the numbers grew. So we can potentially cope with big numbers in computing. You know, we've got processors that do billions of operations per second and multiple processors and big data centers and so on. But what we found was no matter how much computing resources we had available to us, just slightly increasing the size of the problem, say a small increase in the number of cities, meant tens of thousands of times greater resources being needed. Because the brute force algorithm, is a factorial, and we just can't cope with factorials. Now, can we do better than brute force? It's a pretty rubbish algorithm. Let's just hop onto Wikipedia and see what they say. And the answer is yes, very much so. There are much better algorithms than brute force for the traveling salesman problem. And you can go in depth into the maths of it if that's interesting for you. But here's the thing. All of these problems still have all of these algorithms, these solutions, all have that same problem of uncontrollable growth. They might not all be factorials, but they are at least exponentials. So for example, instead of being n factorial, they might be 2 to the n, or 3 to the n, or some other similarish kind of maths. And all of those have that growth issue. So there's a kind of cutoff point. Anything which is like a polynomial. So for example, if we were to play around with this and look at n to the 6, for instance, we can cope with n to the 6. You can see we can put some quite big numbers in for the number of items that we're working with. And n to the 6 is bad, but it's not that bad. Certainly not that kind of bad, right? Which is, oh, did I go up to this one? Yeah, I didn't even show you what would happen if you went to like a big number. You know, that's just an uncontrollable amount. That's the number of centuries it's going to take. So, but n to the 6, yeah, manageable. Not brilliant, but then again, this isn't a brilliant computer here. We can do a lot better than that. But as soon as you go to 2 to the n or n factorial, that's the kind of cutoff point between there and there. So this is a particular class of problems that have that intractable property. So the question is, can we do better? And the answer is yes, we can do. Well, we can't do better. We can't find the perfect solution in anything better than exponential time. It seems. There's a lot of maths, there's been a lot of research, but it seems that's the case. And if it turns out to be not the case, then that's a really interesting problem for various reasons that we'll go into in the next video. So what you can do, though, is you can find a heuristic, like a rule of thumb, that is way better. So a typical example of that would be the nearest neighbor solution. So say you'll start at home and you say, like, I need to find a decent route between these 4 cities. What you say is, like, what's the closest to me? And you say, oh, A, 20 away. And you go to A. And then you go, okay, so now I'm at A, what's the next closest? And it's 25 to C, 30 to B, 70 to D. I didn't put a number for E yet. So yeah, we're going to go to this one down here. What is that? A, B, C, D? It's C. That's C, yeah. And then we get to C, we say, okay, we can't go to A anymore because we've already been there, so what's the next closest one? So it's 90 to B, 45 to D, whatever it is to E. We'll probably end up going to D. So you always go to the next closest one, and it turns out that that is a super quick algorithm to follow. It doesn't have any of those factorial problems, just works an absolute treat. And a lot of the time it's good enough. I mean, if we get back to the real world here, of the travelling salesman trying to find a half-decent route between these cities, unless you're really unlucky in terms of how these cities are laid out, you quite often find that that is the best solution, or at least it's like within 10% of being the best solution anyway. So in the real world, that's what we do. We don't wait several centuries for an algorithm to complete. Instead, we just find something that is good enough, a heuristic. And that's basically the solution to this class of problems, is finding a heuristic. So, in the next video, we're going to look at those heuristics, I guess. Are we? Yes. Oh, sorry. That's where we were. In the next video, we are going to look at some other intractable problems very briefly and think about some implications of these tractability issues.